Welcome to this Chapter 28 video where I discuss locking mechanisms within the operating system, both how the operating system implements locking as well as how the operating system uses locking mechanisms within the hardware. My name is John Jolly. Let's get started. So we need to understand what really a lock is within concurrency. Locks usually are two pieces. You'll have a lock variable. This lock variable contains information such as the lock state, whether the lock has been actually defined yet, whether the lock has actually been locked or unlocked by a particular thread. So this lock variable is necessary. We call this a mutex handle within the pthreads context. Sometimes, not always, but some locks will actually contain a list or a queue of waiting threads, where we actually have the list of threads that are currently blocked, and we can unlock those threads whenever or we can unblock those threads when the lock becomes unlocked and allow that process to continue processing. The second part of locks are the lock APIs. And a lock really is very simple. You can either perform a lock operation on a lock, which is actually a two-step process. The first step in the process is to block the thread execution if that particular lock, the state of the lock, is in a locked state. As soon as it becomes unlocked, this stops blocking the thread, and we set the state of the variable to lock. And the other API is the unlock API, where it actually sets the state of the variable to unlocked, allowing a locked or a blocked process to continue. And then using this waiting thread queue, it's able to move block threads back to the ready or runnable state and allow them to unlock. So with a mutex variable or a lock variable and the lock APIs, we should be able to provide mutual exclusion within a particular thread and allow for critical sections to be protected. So what do we need? There are three things we need to make sure a lock does properly. First is it should provide mutual exclusion. This is the primary purpose of every lock. If it doesn't provide mutual exclusion, it's not a lock. And there are concurrency primitives that provide synchronization but do not necessarily lock or provide mutual exclusion specifically to a critical section. Semaphores are one of those things. We'll talk more about that. So for mutual exclusion, only one thread may hold the lock, and all other threads must block until the lock is changed to an unlocked state. The second quality of locks should be fairness. Fairness means that all threads holding for a lock are guaranteed to eventually acquire the lock. But we'll see that this isn't always the case. You can still have a lock, but if it's not necessarily fair, it's not a particularly good lock. We don't want any threads to starve, meaning we don't want any threads to be unable to get any processing time because other threads keep holding the lock. Finally, we want performance. And there are three things to consider for performance. First, a single thread should be able to lock and unlock efficiently, almost as if no instructions were executed. Also, multiple threads on a single CPU, should resolve lock contentions quickly. And then finally, we should also have a process or a way to allow threads on multiple CPUs to resolve lock contention quickly. And this will be different than the single CPU case, where we need some sort of synchronization between the CPUs. So let's start out. Let's try one hardware solution. We're going to actually do this by changing hardware interrupts. Really, hardware interrupts are one of our biggest problems, either a device interrupt or a timer interrupt. A hardware interrupt will actually cause a context switch. This context switch stops our code from processing. So it can stop code that is in the critical section, in the middle of a critical section, and switch to another context where a lock may be holding or may be getting obtained at the moment. And so if we do that, if a process or if a thread that is in the middle of a critical section is interrupted, that is less efficient. And we have to wait for that particular thread to finish, or the new context switch thread to finish, before we can go back to processing the critical section. So one way to solve this problem is just to disable all CPU interrupts for the duration of the critical section. This is horribly inefficient, especially the way some programmers write code where they'll do entire loops inside of a critical section. And when we disable interrupts, that's everything. That includes hardware interrupts, that includes timers, that's your mouse, your keyboard, your hard drive, your network device. This can really hamper system interactivity significantly. So we really want to avoid any disabling of hardware interrupts. There are times where disabling a hardware interrupt is necessary, and we should take advantage of those times, specifically when we're working within the operating system kernel code itself. Sometimes the operating system code needs to do something when no other device will interrupt, but it should be done very quickly. It should be a very efficient operation. So for our regular programs, this is going to be avoided. We shouldn't allow our programs or user-based programs to simply disable interrupts, because that could get really messy and completely destroy the usefulness of the system. So we've been doing this one for a while now. We're going to try implementing locks using software. So here we have a piece of code where we have a lock API and a unlock API. And the unlock API is fairly simple. It's just simply setting a flag to 0. And the lock API is looping forever, as long as that flag is equal to 1. 1 meaning that it's locked. You can see that it's being initialized up here to 0, but the first thread to come along that locks it will set this flag to 1. All other threads will loop as long as that is set to 1. And then the thread that initially made the lock has to unlock it, which sets the flag to 0. The problem is wasted CPU time. We have here an instance where a process may get scheduled, and all it will do is just keep looping, waiting for this flag to check. And in a single CPU situation, this is never going to change. No other process is going to change this until the operating system times out and schedules another thread. But also there's the problem of multi-CPU systems where this particular check for 1 is being made. Now what happens if 2 threads make this check and it's not equal to 1? Both threads will actually terminate this loop, and then both threads will set the lock to 1, meaning we don't have mutual exclusion at this point. So we consider this code with a race condition, and that race condition simply makes this lock unviable in multi-CPU systems. So our software is not the best solution right now. So let's try another hardware solution. Instead of just disabling interrupts, let's create a instruction in hardware. This hardware instruction does 2 operations at once. The first operation it does is it preserves the old value of a particular flag variable. So it's saving the flag variable. In this case, it's 1 or 0. It is then storing the new value. So it is both reading and writing to this old pointer variable here within one instruction. And then it returns the original value. Test and set is called an atomic instruction. This atomic action happens all within one instruction and cannot be interrupted. When a hardware interrupt happens, if it happens in the middle of this instruction will go ahead and complete before the interrupt is handled. But it's just one machine instruction. And again, do remember that this code here is an example of what's happening in source code. It is not the actual code that needs to be written. This is all built into hardware. So let's go ahead and take a look at how we can implement this. Specifically, let's look at how the xv6 operating system implements this. Here within our within the file spinlock.c, within the acquire function, you've been using the acquire function. This acquire function actually performs a spin loop. So it's not efficient, understood. But one of the other problems was the race condition. And by using this one instruction that sets the value of locked to 1, but checks to see if it was 0 originally. If it was already 1, that means it's locked and will loop again and try to lock it again, try to set 1 to it again. This instruction will repeatedly set this locked variable to 1, and then when it sets it to 1, but the original value was 0, meaning it was unlocked, then the loop will break. You can see the actual machine structure here. In the RISC architecture, it is called atomic memory operation swap. These decide how the swap is going to happen. And all we're doing here is taking this number 1 and trying to write it to A5 and reading the A5 value itself. And so the AMO swap will take care of this operation with one instruction. And then we can go ahead and loop. If it's still a 1, just simply loop back up here to the top of this particular code. So we can see xv6 implements a spin lock using an atomic operation. So this is no longer code with race condition. It is still code that has a loop that is very inefficient. So there must be a better way to do this. There are other hardware atomic operators. We have compare and swap. Compare and swap is like test and set, but will store a value only if there's a match. So if we come back here, a compare and swap would say, okay, look at this variable, compare it, see if it's a 0. If it's a 0, put in a 1, and then go ahead and respond to it in the loop. It's a bit more efficient that way. So this is frequently what systems will use when they want to really do a lock. Other hardware architectures will support what is called load link and store conditional. In this particular case, the store operation, or store conditional in this case, will actually fail if there's been an update anywhere else in the system since the last load link. So first, a piece of code will execute a load link, which really just loads a variable from memory. But then when it goes to store a value in memory, it will attempt to do a store conditional. And if this store conditional fails, then you just simply go load the variable again, or the value from memory again, and then try the store again. And just keep doing that until store conditional is successful. Another instruction that's very useful for synchronization is fetch and add. It's again like a test and set, but what it does is it actually retrieves the value from a piece of memory and then increments it. So it's setting a new value. This is a really good way to allow each thread to have a unique order number to their particular thread. That way, or to their particular lock. So if you have 3 threads that are blocked because they're trying to lock a mutual exclusion that's already been locked, you can actually have the order of that of each thread stored within the lock. and have the thread be able to say, okay, it's my turn. I can see that this variable has reached my particular value that was retrieved with the atomic increments testing set. So it makes the locks fair. So what can we do? So we fix the race condition with machine hardware. How can we fix the spinning problem? Well, there are a couple ways we can do this. The first is just simply yield the processor during the spin lock. So within the spin lock loop, call a yield instruction, which actually causes the operating system to schedule another process. This is still expensive because there are context switches, and frankly, each time that process is the thread that is blocked is scheduled, it's going to have to yield again. It's going to spin still, but it's going to spin less. Plus also, as we know, scheduling is unpredictable, which means we might have one particular process that never gets scheduled because two other threads are constantly locking and unlocking the mutex. So yield is a good way to do this, but it's not efficient and it's not necessarily fair. A second way to do this is to actually have in your operating system a park operation, which causes the thread to be added to a wait queue. So it's added to a list of threads that are blocked on a particular mutex. And those threads will not be rescheduled until some other thread, the thread usually that's called unlock, calls unpark for a particular thread. And so the thread that is unlocking checks the queue and says, okay, who's next? I will unpark that particular thread. And then that thread is allowed to execute, and it will see that the lock has been unlocked, and it will be able to continue. You don't have unnecessary context switches, and it still spins, but only when the lock variable is accessed. So it's not very often. So these are the actual park and unpark are fairly common operations within mutexes in operating systems these days. One last thing we need to be aware of when it comes to threads, it's very important, is the concept of priority inversions. So this happens when you have a system that has different scheduling priorities. So you have one priority that has one scheduling queue, and you have a lower priority that has a different scheduling queue. And as you remember, in a multi-level queue, if a higher queue has a process, it will be executed before any lower priority processes can be executed. If we have two threads, let's say we have thread 1 and thread 3 here. Thread 1 is a low priority thread, and it acquires a lock that is shared with thread 3. If thread 3 comes in and is scheduled, it will see the lock is set, and it will actually be forced to spin, waiting for thread 1. But consider here, it's spinning doing nothing. The operating system interrupts that thread, says, okay, there is still a thread in the high priority queue, and goes right back to scheduling that high priority thread. Thus, this is causing the low priority thread to starve, and the high priority thread is not continuing. This is a priority inversion where we need to get the first thread to actually execute. Now, as you're aware, any proper multi-level queue will actually reset the priorities of all threads and allow them to run equally for a time. So in a good multi-level queue system, this shouldn't last long, but it's still inefficient and is a waste of resources. If we have 3 threads, it doesn't matter what happens on a multi-level queue. If we have thread 1 that acquires a lock, we have thread 2, which is a medium priority thread schedule. It will preempt thread 1, not allowing thread 1 to unlock. High priority thread will be scheduled, but it will not be able to do anything. It's going to spin as it waits for the lock. And of course, thread 2 will be allowed to run whenever it will be allowed to be advanced when the multi-level queue advances those. But this prevents thread 1 from actually accomplishing anything. Even if we don't spin lock in 3, let's say thread 3 yields its CPU time, allowing thread 2 to execute. Well, if thread 2 executes, it's still not allowing thread 1 to advance, meaning that thread 2 is running more than thread 3 is. Thread 2 has priority above thread 3, which is supposed to have a higher priority. In this particular case, we have thread 3 starving for CPU time as well as thread 1, while a medium priority thread is doing work. This was actually the case on a Mars rover, the Pathfinder rover, where from 20 minutes communication distance, the rover kept resetting. Well, it reset because there was a process called a watchdog process checking to see if a high priority process was doing its job. And when that watchdog discovered that that high priority process was not running, it would reset the system, reload the operating system to be able to get that high priority thread running again. Well, it turned out thread 3 was suffering from priority inversion. The way they fixed this was anytime thread 3 blocked waiting for a lock. So when thread 3 attempted to acquire a lock and had to wait, it would actually identify the process that was holding the lock. And what it would do is it would move that process, in this case, thread 1, to a higher priority, to an equal priority level temporarily, until this thread unlocked, until the low priority thread unlocked that particular lock. This gave the low priority thread high priority status to finish, and then thread 3 could continue. So this is called priority elevation, and priority elevation helps solve a priority inversion, both in this case as well as the spin lock case. This brings me to the end of this chapter 28 video, where I talk about locking in operating systems.